This is Milo. He is 3.5 years old. Milo is going to help us learn about SD.
See, SD uses natural deduction, like we said in the last video. So the rules are formalized versions of logical reasoning in ordinary language. And some of these rules correspond very closely to rules that you will find people making explicitly in, or inferences that you will find people making explicitly in ordinary reasoning. Um, but many of them aren't. Some of them are like bookkeeping rules. They're simple steps that we are actually making when we're reasoning, but we don't make explicitly. But remember, SD is like a ladder, right? And we need to, like a ladder, you have to have all the steps there. So we have to have all of the steps in the reasoning made explicit in SD. So these are not things that are explicit in ordinary reasoning, but they are things that small children will do explicitly. And so it is useful to learn a little bit about, logical reasoning from a 3.5-year-old child. So we'll start with the rule reiteration. Let me just say something about what this means here. So this defines the inference rule. It says that if you have this on previous lines of a derivation, then this little wedge arrow thing here tells you what inference the rule allows you to draw. So if you have P, any sentence of SLP, on a previous line of the derivation, then you can infer P. This is the basic argument strategy that young children use. So, for example, we're sitting at the dinner table, right? And, Milo is, sitting there and he says, Daddy, me is want dessert. And I say, well, you haven't actually eaten anything. You just sort of moved it around on your plate, right? And rearranging is not the same thing as eating. And so Milo then applies the inference rule of reiteration plus more volume. And he just says, Daddy, me is want dessert. So we'll formalize this argument. So we'll symbolize, here's our symbolization key, right? So D will stand for Milo wants dessert. And then the argument goes like this. So line one, we introduce D as an assumption. I mean, from the point of view of logic, this is an assumption. And then you have D, right, which is inferred from line one by the rule of reiteration. I mean, this is obviously a circular argument, right? Because it's just the same line repeated. What the reiteration rule is actually for is something that we'll come back to in later videos. Like the purpose of the rule in SD is to make sure that all the lines that you have are in the places where they need to be in your derivation. Okay, the next rule we'll look at is conjunction introduction. So if you have P and Q, these are two sentences of SL that are on separate lines, then you can infer P and Q. And this is another bookkeeping rule. This is something that, I mean, it's an inference that we make. It's not something you ever really explicitly state in ordinary reasoning. Okay, so here's an example. I wake up in the morning and, I get up and I find that Milo has gotten up before me. So I go stumbling into the living room and I find that there are little cars strewn all over the living room because, he's 3.5, right? You give him like a box of little cars, right? And it will take him approximately 4 minutes for the box of little cars to end up like, everywhere within a 40-yard radius. And then on top of that, this is laver in the picture, right? Dried seasoned seaweed. Milo absolutely loved it. But if you chew it up and it doesn't all end up in your mouth, then what you get are little pieces of green shrapnel that just sort of fly everywhere. So I go in and I find that he's been eating seaweed on the couch again, and so there are tiny little pieces of seaweed all over the couch. So I say, "Oh, there are little cars all over the living room. Is that seaweed? There are pieces of seaweed all over the couch." And I go, "Milo, there are little cars all over the living room and pieces of seaweed all over the couch." So Here's our symbolization key. We start with these two assumptions. There are little cars all over the living room. There are pieces of seaweed all over the couch. And then here is our inference. There are little cars all over the living room, and there are pieces of seaweed all over the couch. It's a very, complex, very deep philosophical argument here. Now it's really important to note, right? Derivation rules in SD, they only apply to entire sentences, right? They never apply to parts of them. So, like, look at this argument here. I am on Earth or on the moon. Salmon are fish. Therefore, I'm on the moon. Right? Here's how you symbolize it in SD. Right? You cannot use reiteration to infer M from this line, E or M, because M is not a line by itself, right? It's not a sentence that has been asserted on a previous line. It's a subcomponent of E or M. So you can't pull it out you can't pull a subcomponent out of a sentence that it is with reiteration. Reiteration just allows you to take an entire line and duplicate that somewhere lower in your derivation. You can't use that to pull out a fragment of another sentence. Right. Similarly here, right? If Milo owns a Jaguar, then he must make more money than I do. Salmon are still fish. Therefore, Milo makes more money than I do, and salmon are still fish. So you can't have this here, S, on this line, and then this subcomponent here, that is the consequent of this conditional. You can't use conjunction introduction to join those two together to get this conclusion. Right, that again, you can't access the subcomponent. You can only apply conjunction introduction to entire sentences that are on lines by themselves. All right. This is conjunction elimination. This is another bookkeeping rule. Here, there are two versions of the rule, right? So if you have P and Q, right, so the initial conditions for the rule are the same, then you can infer P or you can infer Q. So the rule is symmetrical, right? If you have a conjunction, you can infer either of the conjuncts according to the rule. Okay, so here's the scenario. Milo and I are in the grocery store, and we pass by the toy aisle, and he notices it before I manage to distract him, and he says, "Me is want a toy." I say, "Well, we're not here to get toys. We're here to get groceries." And he says, "Oh, but me is need more toys." And I say, "Well, no, you don't. You definitely do not need more toys." And he says, "Me is need more toys because me is have only 14 toys, and me is need more toys." Notice the argument marker because here. Milo's father is a philosophy instructor and his mother is a lawyer. So this kid learned how to construct well-formed arguments at a very young age. Okay, so the inference here, this argument actually you can reconstruct a couple of different ways. But here is one way of symbolizing it, right? You have FNN, right? Milo has only 14 toys. 14, incidentally, this is the biggest number that he knew at the time. So he has only 14 toys and he needs more toys, therefore he needs more toys. And then the derivation goes as follows. You have FNN as your assumption, and then you have N by conjunction elimination. Now here, it's really important to remember that you can only apply this rule, conjunction elimination, to a sentence where the main connective is and. So you have to pay very close attention to the main connectives of sentences to make sure that it is actually a conjunction that you're looking at. So take this, for example. If the windows were all open, I would be freezing and so are you. Therefore, you are freezing, right? This is a transparently invalid argument, right? If the windows are all closed, we're sitting in front of a fireplace, right? We're not freezing. Even if it's true that if we did open all the windows, we would all be freezing. Right. When you put that in symbolic form, though, people will get thrown off and think that, they forget that the horseshoe here, that is the main connective of this sentence. which means that you can't apply conjunction rules to this, right? This conjunction is embedded in a subcomponent of the sentence over here. So you can't apply conjunction elimination and pull that out and get it down here, right? What you can do, you could apply conditional rules to this if you had other things that allowed you to do that. We'll look at conditional rules in a later video. But you can't apply the conjunction rules to it. So this is not a correct derivation, which models the fact that this is not parallels the fact that this is not a valid argument. So those are the rules: reiteration and the two rules in SD that govern conjunctions.